Hello everybody and welcome to the second part of the Python for Programmers talk, also known as Beginner's Night around here. The URL here is where you'll be able to find all of the slides for this talk as a PDF, so easy to check. If you want to write it down, this would be a good moment. Okay, now, this is a description of the audience of this talk. A bit less crowded than the one I imagined when I wrote it. But you're experienced programmers. You know what programming means. Maybe in C, maybe in Java, maybe in Ruby. You have some modest previous exposure to Python, like we did in the first night, which is here. Unfortunately, it looks like the video of the first night of Python for Programmers didn't actually make it to Google Video. There is, however, a video of another talk of mine using roughly the same set of slides, pitched very differently because I was talking mostly to an audience of my colleagues at Google. Don't try to write this down. Use the aliaxit bp_bat Inc. and you'll find this on the second slide. Some parts will be very fast and technical, and I apologize in advance. The formatting, the choice of names and idioms and so on is kind of constrained by the fact that I want to fit complete examples on a single slide. So don't imitate this style unless you have to program on slides as well. Okay, also shameless self-plug. Some of the examples are adapted, simplified, and without all the wonderful discussion, which you should really definitely read in this book, by the book co-edited with my wife, Anna, second edition of the Python cookbook. Alrighty, so we have built-ins and we have libraries. The built-ins are always accessible anytime you use Python. And the crucial idea behind a built-in is that you should never call a special method directly on an object. I mentioned that in the first part. We make the name of special methods ugly on purpose, so as to deter people from actually going and calling them. So for example, if you want to know the absolute value of a number, you do not call x.__abs__, open close. You call abs of x using the built-in abs for absolute value. Why is that important? Well, because the built-in can implement a sort of template method design pattern. It can try to see if the object has a special method for absolute value. If it doesn't, maybe it can compare it with 0 and try to change sign if needed. It can do a lot of things in a predetermined order to get your result. So never call the special method directly. Use any and all of this enormous list of built-in types and functions, which will then proceed to present with a bit more order. They're just in alphabetic order here. Note that these aren't all of them. There's many more. These are those that you really should know to be good Python programmers. And if these look like a lot, you have to consider there's many more, both functions and types, in the standard library and in third-party Python extensions. And we'll see a lot of the built-ins, several of the standard library stuff, and some mention of third-party extensions. So for non-built-ins, for anything you get from the standard library or a third-party extension which you have installed, you have to use either the import statement, import module name, or the from statement, from import module name. I suggest very strongly as a Python best practice that what you have after the word import, whether it's the statement or the close of the from statement, is always a module name. Python lets you import just about anything, but don't. It's very confusing to the reader of your code if you import some modules, some classes, some functions, and then just use them. Just import the module, and then use the normal syntax module name dot function name to access the function within the module. If that's impractical because the module name is very long or because two modules from different packages conflict, you can change the name with which you refer to it with the as something clause and then use the something instead of the real name. Note that I break these rules in these examples for the usual reason. I really want to be compact and fit a lot of stuff within every slide. So a very old but still valid slogan for Python is batteries included. The standard Python library is very rich. Probably nowadays is not quite as rich as the Java library, but when the idea was coined like 10 years ago, there was no language around with a standard library as big as this. There's so much stuff you can't really think you can memorize it all. There's 190 top modules, 13 packages with 300 modules in them, plus encodings, unit tests, and demo and tools, which contain a lot of extremely useful code as well. And I've always, demo and tools need not be packaged with predefined distributions of Python. So something I always suggest to anybody learning Python, no matter what you choose to install it, or if it comes with your machine, like it does with Ubuntu and many other Linux distributions nowadays, or it does with Macs of all sorts, get the sources as well. Just the ability to access all this stuff in demo and tools is well worth the little inconvenience of a download. But this is just what's included with Python. There are other batteries, plenty of other batteries. The official URL nowadays is pypi, which isn't particularly catchy. The name of the thing used to be the cheese shop in reference to a Monty Python sketch. However, it was always a very inappropriate reference because the point of the cheese shop in the sketch is that it's very clean, but it doesn't actually have any cheese, while pypi does have a lot of packages, each of them one or more modules. I noticed the first time I prepared the very first version of this talk a few months ago, that was April, I checked and it was the day of destiny. We had exactly 2,222 packages registered on the cheese shop. I checked yesterday, actually, not today, and exactly 400 more. So I like round numbers. So that's exactly 4 months, exactly 400 packages more. So we're growing at exactly 100 packages a month. So that's easy to explain and to remember. And unfortunately, the classification doesn't really help much. Like, more than 1/3 are classified as software development. Well, yeah, every piece of library can help me do software development. That doesn't really help. Okay. But nevertheless, there's plenty of interesting stuff, including, as is typical of these repositories of third-party modules, many ways to approach a single problem, which is very un-Pythonic. Unfortunately, there is no central authority saying, okay, so there are these 7 packages to do graph processing. We'll pick this one. All 7 are going to be there, and you'll just have to have a look for reviews, give them votes, and so on. So at very superficial level, what are all of these third-party extensions? Well, there's a lot of graphical user interfaces, databases and wrappers for databases, a lot of computation stuff, lots of network-oriented and web-oriented stuff, development environment and tools, stuff for games, multimedia, scientific visualization, integration with all sorts of languages, and more. And much more. Like, for example, nowhere in here is written, what about the thing that lets you control OpenOffice from Python, script all of the OpenOffice application for Python? Well, it doesn't really enter any of these, but it's still there, as are 2,000 more. So what do you do with a third-party extension? You have to install it on your computer. There are several approaches. The most traditional one is you unpack it, typically a tar.gz or zip file. It contains a setup.py file, and you just run this with your Python and the install verb. And if, depending on how your machine is installed, you may need to become root or use sudo if the Python installation is placed in a directory where you can't write. The most modern idea is eggs, not necessarily this kind, which are part of the setup tools. Some people love it, some can't stand them. And I plead the fifth about which my idea is. For Windows, many packages come with self-installing program like .exe. These are very popular in the Windows world. And similarly, for the Mac, you may find packaged as disk images, and so on and so forth. And for Linux distributions particularly, a lot of the most popular packages come in the various .deb or .rpm formats of the various distributions, so you can use apt and get. For Mac in particular, there's a repository of pre-built stuff. You don't really need it because every Mac comes with a great C compiler for free, but people often don't install it, so you may want to use this. One way or another, you've got to get the extension installed. And now, finally, we get into the meat of the library. We start with the most elementary type, numbers. Python has several built-in types of number. Int and long, this is a distinction which is traditional. The int is whatever fits in your machine word, typically 32-bit or less, and the long is anything else, limited only by your available memory. The distinction will collapse in Python 3000. Every integer number will be able to grow as much as needed. And it's still it's already kind of like that, but like if you ask for the int of 999 to the 999 power, obviously it doesn't fit in 32-bit, it gives you a long. Even though you've asked for the int, it gives you the long anyway. Float are actually double precision floating point number, and complex. As an old Fortran programmer, I never understood why most languages forgo the wonders of complex numbers. Notation is like digits, and if there are few, you'll have an int. If there are too many, you'll have a long. You can use hexadecimal, you can use a dot to make a floating point number, and you can use the plus and the j to make a complex number. The operators are arithmetic and bitwise, more or less what you'd expect. Star star is raised to power. Again, as an old Fortran programmer, I don't understand why most languages don't have an operator to do raised to power. And the double slash is divided with truncation. Well, the single slash, at least in Python 3000, will be without truncation. Right now, to have division without truncation between integers, you have to use the from future import, which we saw last time. Several built-ins are targeted to number. We've already mentioned abs for absolute value, minimum and maximum. You pass them a sequence of numbers, and they give you the smallest or biggest respectively. Of course, if you try to use min and max on a sequence of complex numbers, they will raise an exception because there is no such thing as comparison greater and smaller in complex numbers. POW is like the star star, but it has a three-element form to do exponentiation modulo something. Round applies to float, rounding them to a certain number of digits. Sums a sequence. The standard library has several modules, such as math for like trigonometric function, logarithm, exponentials, and so on, and CMath for the same thing applying to complex numbers. And it also offers another type. Decimal is the name of the module. Decimal with the uppercase. D is the name of the type, which is a floating point decimal number, while standard floating point is binary. So basically, it gives you a well-known number of digits, which may be very important, particularly if you do financial computations. And it supports exactly the same operators and built-in functions as any other kind of number. And it has some methods, like the SQRT method gives you the square root as a decimal. In the third-party world, there's plenty of number stuff. I point out Gimpy because it's my baby. It's a module for unbounded precision computations. It's got integers, rational, and floating point numbers with unlimited number of bits. Of course, it does things in software, so it's going to be slower. And it's got, again, support for all the same operators. So if you are summing two numbers, you're going to use plus, whatever kind of numbers they may be, and a lot of method and function. And there's plenty of other stuff that you may be interested in. CLNUM is essentially covers the same space as GIMP, but it's implemented in pure Python. Very nice for learning the algorithms behind infinite precision arithmetic. GIMP is very much faster, of course. DMath, and there are other alternatives, adds math. It's kind of like math and CMath, but applies to decimals. So you can do sine and cosine in decimal if you need to. Pipel adds polynomial as a number type. This also adds rational functions. This adds some other kind yet of complicated functions. Let's just give you one very simple example. One typical thing you may want to do if you're into number theory is compute the factorial of a number. This is sometimes thought of as an expensive operation simply because the results tend to be a bit big. For example, the factorial of 210 is the following 399-digit numbers. GIMP has a fact function to compute factorials. And how long does it take? With the timeit module, we can import it from the standard library and use it to measure speed. To do 1,000,000 of these computations, 29 seconds. So computing the 400 digits factorial will take you about 29 microseconds on a typical laptop of today. If you have a good machine, it will be less, of course. But for a laptop, it's not too bad. Another elementary type, which is extremely important, right next to numbers, are strings. Python has two types, string proper or plain, which uses bytes, and Unicode, which uses Unicode characters. And that is unfortunate because it complicates things a bit, but it's a legacy aspect. We started out with only single byte character strings, and now we've added the Unicode ones, but keeping backwards compatibility. Python is always very keen on that. The whole point of Python 3000 is that it, being a major release, technically is 3.0, it can and will break backwards compatibility. So strings in Python 3000 will be exclusively Unicode, like in Java, making the language much simpler. So what can you do? How do you denote a string? With single or double quotes, it's irrelevant, or as a row, which means escape sequences aren't expanded, like \n in a normal string, stands for one single character, which is end of line, like in C. But if you want this to mean the character \/ followed by the character n, you can use it as a row. And the U version of all of these give you Unicode strings. You can concatenate to string by summing them. You can multiply a string by a number to have a certain number of repetition. You can format string with a very rich format language, which is kind of like printf. This is rather unPythonic. In Python 3000, instead of this, we'll have a format method on string objects, taking a simpler language. The built-ins are, for you, those of you with a Pascal background should recognize it. CHR, given an ASCII code or returns a character, ORD, given a character, returns its ASCII code. Actually, ORD also works on Unicode characters. To produce Unicode characters from its Unicode number, you will use UniCHR. Strings are read-only sequences. They're not exactly containers. You can put things in there, but they're sequences, meaning you can go, how long are they? You can do indexing and slicing like on other sequences. You can loop over them. And they've got so many methods, I've lost count. Capitalize returns a copy of the string with the first character turned into uppercase. Center returns the string padded with blanks to be centered in a certain field. Standard library is full of interesting modules to deal with strings. String itself has something useful. RE gives you regular expression, very close to Perl's. Struct lets you pack and unpack binary values into a string. Sysstring.io lets you use a string as if it was a file, so you can like write into it and then get the value or read lines from it or something like that. Text wrap lets you format strings, like flowing paragraph things. Codecs and Unicode data give a lot of preparation for transition between Unicode and byte representations, or analysis of a Unicode string. What kind of characters does it contain? And string prep takes, essentially implements the RFC about string preparation for network travel. And again, there's plenty of third-party stuff. Some of it is very funny, like Anagrammer, which is a module to help you do anagrams given various possible dictionaries. It supports many languages. To the extremely useful, like LuPy, is a Python-compatible interface to Lucene, which is a very popular open-source search engine. PyNum2 Word, you give it a number, and it spells it out in words, which can be fun or useful. PyStemmer, you give it words, it extracts the semantic stem of the word, so singular form, base form of verb, and something like that. And of course, a huge amount of XML processing. That's technically text, but not all that significant. When you make a big string from pieces like this bolo strings here, if I could say just one thing to a new Python programmer is, do not ever code this. Never, ever. Forget it. It doesn't exist. Forbidden. Why not? Well, if you are into Java, you know that you don't code this in Python for the same reason you don't in Java. Strings are immutable. Every time you do the big plus equal p, the old value of big gets thrown away, and a new value of big, new string, gets constructed and bound to that name. So the first time, say you're doing character by character. First time you allocate and copy one character, then two, then three, then four, then five, then six. Each of these is a pretty costly operation because there's a free and an allocate, plus the total amount of bytes you're copying is 1 plus 2 plus 3 plus 4, sum of I for I from 1 to n times n plus 1 halves, minus 1 halves. So you're doing a quadratic amount of operation if you ever code this in Java or Python. So don't. You just take the sequence of pieces, make it up if you need, build a list. Building a list is very fast, appending to a list is constant time. And then you join them. Use a join method of the empty string. And if you really hate this, you could use string.io, but my wife was horrified when I mentioned that, so I don't think I'll get deep into that. Moving on from elementary types, such as numbers and strings, we have an ample choice of container types. The most elementary one, because it doesn't have any method or anything, is the tuple, normally denoted by parentheses, though the parentheses are generally optional, or you could do it with a keyword, with a name of the type, tuple, and commas, which are what really denotes the type. Note the need for the comma here. Open paren 23, close paren is not a tuple, it's an expression which is worth the number 23. The parentheses are just overloaded to mean arithmetic precedence. The comma is what makes this a tuple. And the parentheses might not be needed. If you write a equals 23, comma, a takes a tuple. The fact that there are no parentheses is irrelevant. The parentheses are not syntactically necessary. Lists are maybe clearer. There are mutable sequence. So the name is a bit tricky for some people. They're not linked lists. They're a compact in-memory structure, kind of like a vector or array, if you want. And there is no need, although you can have an extra redundant comma at the end. That's permitted, but it's not necessary in this case. Again, you can call the type to make one, like a constructor, so to speak. Set and frozen set. Frozen set isn't very often used, but it's an immutable version of the set. But set is a simple hash table. So the items need to be hashable, which normally means immutable, like numbers or strings. And you either, and this one doesn't have a special notation, it will in Python 3000, but not now. To make an empty one, you just call it without any argument, as you could do with list or tuple. If you want, list open paren, close paren means an empty list, just like open square bracket, close square bracket. Or you can pass it any sequence. Note that if we didn't have the comma here, it would be an error, because you cannot make a set by passing it a number. You have to pass it a sequence of numbers. So in this case, we're passing a sequence of a single number, a tuple with a single element. Or, of course, you can pass a string, which is a sequence of characters. A dict, short for dictionary, is also a hash table, but a hash table used to do key-to-value mapping. So it uses braces as a constant notation and colon to separate the key from the value and commas to list them. Or if you want to call the type, you typically pass it keyword arguments. This uses CI, two-character string, as the key, AO, other two-character string, as the one value corresponding to that one string. All containers support len. Yes?
Does the CI need quote marks?
No, that's a big point. This is keyword notation, so no quote marks are needed. Actually, they would be syntactically incorrect. I'll get back to that. Len of a container is the number of items it contains. You can always loop on a container, and you can always check if something is a member of the container with a if in. What this means is pretty obvious for tuples, list, and set. For dictionaries, both the looping and the membership testing are only about the keys. So if 23 in this dict means if 23 is a key in this dict. It doesn't go and look at the values, only at the keys. And similarly, for x in dict will give x all the values, all the keys in the dictionary one after the other. The order in looping on either a set or a dict is just about anything it wants because it's a hash table. It doesn't bother with order. Except for tuple, the rest have a lot of very useful methods, and sets only, and frozen sets, also have operators because it's sometimes a more natural way to use them. For example, to do the union of two sets, you can use a vertical bar, which used on integers, it would be the bitwise OR. Used on sets, it's union. OK, how do you make a list? This is a little recipe, pretty important. You don't do this. This would take the list containing the single item 0 and repeat it NC time. So that gives you one list with NC zeros. And so far, so good. But then if you multiply that, make a list of that and multiply that by NR, then you get NR times the same list, which is hardly ever what you want. With this, the list comprehension notation, you get new list for every row. You don't need it both ways, so if you don't mind the asymmetry, this is also perfectly acceptable. Another trick which is very important, if you want to make a list of words containing no spaces, that happens very often, this is the canonical way. But note that my favorite way, which is to just have the string and split it, is a bit shorter, which is very important when you're fitting code on slides. Actually, I find this more readable because it has less punctuation. This form has plenty of, it has the brackets, a lot of quotes, the commas. I really like this. So much cleaner. Now, tuples, as I mentioned, you don't really need to have parentheses, just commas. And one thing they're useful for is just group a set of fields. In this case, first name, last year, name year, you can unpack them by assignment. The advantages of tuples over lists is mostly that they can be elements of sets, keys in dictionaries, and so on, because they're an immutable container. To make a dictionary, this is the standard form, but if all keys are valid identifiers, you can use the keyword form. I personally find it more readable, but again, that's only me. It's got less punctuation, which I like it. If you want to use attribute syntax for access, to access this, it would have to be D, open bracket, quote, ZIP quote close bracket. A little bit too much punctuation. If you use this trick from the cookbook, you can then access b.zip. The only problem is that all the keys need to be valid identifier. So for example, if one of your keys is the word print, you cannot do this, because print is a keyword in Python, so you cannot use it as an identifier. Operation you often want to do is not just go and get the value, because, and if it's not there, we'll give you an exception, but get it if present and get something else if the key is not there. Dictionaries support this directly. The get method of dictionary takes the key and a default value and returns either the value corresponding to this key or the default value if the key is not in the dictionary. For a list, you must implement it with a small function, and there's two approaches. One is just try doing it. Just try returning the ith element. If this gives an index error, well, the index is outside the bounds of the list, and only then return default. This is very elegant and compact. Unfortunately, it's really only acceptable if most times either you don't care about speed, which is in some cases a possibility, or almost always the index will be OK. And it's only going to raise the exception a few cases, because raising exception and catching them isn't exactly fast. This alternative is less elegant, takes more reading, and so on. But if you have a lot of cases in which the index will be out of bounds, this will be much faster. Note that the index can be up to negative len included, or up to positive len excluded, because the index go from 0 to len minus 1, meaning left to right, and then start counting minus 1 to minus len when you're going from the right. So to copy objects, to copy just about anything, you can import the standard library module copy and just call copy copy. That's a shallow copy. It's a copy of the container, but all the items contained are identical, which doesn't matter if they're immutable, like numbers or strings, but sometimes could be confusing if you're basically sharing two references to the same, for example, set. For those rare cases where you really want a complete duplication of the graph of objects contained and so on, you will use deep copy. Be warned, it will take a lot more memory and will be much slower. Another possibility is if you know exactly what type you want in return, copy copy goes to quite some trouble to find out exactly what type X is and give you another X. If you know you want a list, it's much simpler to call list of something. If you know you want a set of something. If you know you want a dict of something. If you know you want a tuple of something. I'm sure you can generalize from here. And in this case, it doesn't really matter if what you're passing is at the type. It guarantees a return value, because it's like a constructor. Some people like a weird syntax, which Python happens to support only for lists and tuples, which is open bracket, colon, close bracket. I don't think it makes any sense to use it ever. But I warned you because you may see it in existing Python code. I think calling list of the other list is so much more readable and pronounceable. Just imagine reading your code over the phone. Also, you can call all the types without any argument to make a new empty container. That's maybe not as important because, to be honest, open square bracket, close square bracket is a perfectly acceptable way to indicate a new empty list. But this is OK too. So strings, tuples, and lists are sequences. Dicts and sets are not, because essentially they're not really order sensitive. They're in any which way. The order doesn't really matter. But strings, tuples, and lists are in a certain specific order, which is exactly the order in which you've built them, and so they're sequence. Every sequence can be repeated and concatenated, as I mentioned earlier for strings. They can all be indexed, and that also goes for dicts, but In the case of sequences, the index is always an integer. It can be 0 to len minus 1 as a positive index, or negative to an index from the right. They can also be sliced. You can pass 2 indices with a colon or 3 indices with 2 colons. And this basically means from the first one included to the last one excluded. And in the 3 form, you also give the step at which the indexing must proceed. So for example, chow of 2 is A, 0, 1, 2. Indices always start from 0. Chow of 3, 2, 1, minus 1. Let's work it out together. What's 3? It's O. It goes by a step of minus 1, so backwards, up to 1 excluded, so OA, and that's the result. The fact that the first bound is always included and the last bound is always excluded is one of the best principles of programming. I met it first in the late 70s, early 80s, in Andrew Koenig's book, C Traps and Pitfalls, and I really, really suggest you read it because it's a great piece of advice. Python does its best to almost always impose it on you. List are mutable sequences, so you can assign to the indexing of slice. The assignment to slice can change length because you can have on the left of the equal a 3-element slice, on the right a 7-element slice. It will stretch the list to fit things in. That doesn't apply to extended indexing. That needs to keep exactly the same length. And as I mentioned, that doesn't apply to Dixon sets. Okay, so let's see some example of these. This is a looping over index and something iterable. I've seen many people code, because they come from languages where loops are mostly things for integers, for I in range of len of a list, item equal a list of I, blah, blah, blah. This is not good. If you need the index, then loop over the enumerate of the list, which is the pair of index value, index value, index value. And then you have the value, for example, to check, and you have the index, for example, if you need to assign back there. A good alternative, of course, is a list comprehension. Just build a new list. In this case, we could use the if-else ternary construction of Python 2.5. I don't find it very readable, to be honest, but I guess it's only been a few years, so we'll eventually get used to it. It's what happens if the condition is satisfied, if the condition else, what happens if the condition is not satisfied. All containers are iterable. Other things are iterable too. Genexps, generators, all stuff we saw last time. And the built-ins are defined to work on iterables. So you don't have necessarily to know what kind of iterable you're working on. The built-in will deal with that just as you could if you did a for item in whatever iterable this is, colon. I already mentioned most of the constructors. There's a frozen set, which I just barely mentioned, range to make a list that goes essentially like a slice, from something to included to something excluded by some step. X-range is almost like range, but not quite, because it's not a full-fledged list. It's something you can only use as an iterable. There's many accumulators which take an iterable and boil it down to a value. For example, all. All takes an iterable and checks the truth of its items. We mentioned the concept of truth testing last time. If every single item in the iterable is true, then all the iterable is true. If even one is false, then all immediately terminate and is false. So for example, you want to check that every item in a list is greater than 7, all, open paren, item greater than 7 for item in list, close paren. This will return true if and only if every single thing in the list is greater than 7. Similarly, any returns true if any of the items in the iterable is true. Otherwise, as soon as it finds a false one, it returns false. I'm sorry, vice versa. As soon as it finds a true one, returns true. Otherwise, if it gets to the end and none was true, then n is false. So any of an empty sequence is, who thinks it should be true? Who thinks it should be false? 99%. Yes, it's false. There isn't any, so no, false. There's nothing. Is there any policeman higher than 7 feet? None? No, empty sequence, so no, false, obvious. All, vice versa, what should all be for an empty sequence? Who think it should be true? Who think it should be false? Okay, a bit more confusion here. Are all policemen with a green skin taller than 8 feet? Well, there aren't any policemen with green skin. That's the assumption. So can you find a single counterexample of a policeman with green skin that is? No, you can't. So all of an empty sequence is true. So len, we already mentioned, is the len. Max and min are the highest and lowest, and sum is the summation. Be careful about sum, yes?
I have a question on len. Does it calculate len of a sequence, or does it remember len?
It doesn't actually work on every iterable. It only works on iterables that expose the special method under, len, under.
Then
it just asks the sequence, how long are you? The sequence is supposed to, yes, sequence is supposed to. If the sequence doesn't cooperate, then you get an exception.
I was asking because I was curious about your list get methods that you do, 2 of them. One of them called len twice, and yet it was faster than the try except.
Oh, yeah. It's calling a simple built-in that just calls the special method in the object is very fast. Takes nothing. Yes?
Is there a perfect hash, like frozen dict?
No, there isn't any mutable version of dict. Not in the standard library or built-ins. Okay. So sum is intended to sum a list of numbers or sequence of numbers. I've seen people use it to sum a lot of lists. That is not good for the same reason for which it is not good to make a big string out of small pieces by summing. You should use extend in the case of list, and you should use join in the case of strings, and so on. Sum is really intended for a sequence of numbers. Indeed, if you don't pass it an initial value, it uses 0. So it works fine for sequence of numbers, and that's what all it should be used for. Okay, I've already mentioned enumerate. Iter simply takes any iterable and returns an iterable. Basically you can make multiple iterators on the same list, for example, by repeatedly calling iter, and they will on the same underlying list, they will advance independently. Map is a bit complicated and kind of but it basically calls a function on every item of a sequence. Reversed gives you the reversed sequence. Sorted gives you the sorted sequence. Of course, the items must be comparable. And zip takes 2 or more sequences and gives you the sequence of tuples, 1 per. So here's a few examples. Frequent task is to invert a dictionary. So as long as you have the dictionary with values which are also hashable and are unique, there's no duplicate value, this is the simple way to invert a dict. The iter items method lets you iterate one after the other on the key value pairs. So we loop on key value, and we simply want value and key swapped. Of course, if the dict is not unique, then this would basically associate to the value arbitrary one of the many keys mapping to it. That's hardly ever what you want. And you can do it in other ways, like build a dict of list and so on, but that's not exactly inversion, so this is inversion. Another possibility, yes?
Why would you use iter items instead of just items?
Items returns a list. Building a list only to iterate on it is wasted effort. If the dictionary is very big, the amount of memory that it needs to allocate to build the items can be proportionally just as big. In Python 3.0, a crucial simplification, all of these methods will return iterables, kind of like looking a set immutable or read-only set rather than a list. Originally in Python, a list was basically the only type of sequence, and so it was very natural to use that. Okay, this basically builds a dictionary from the list so that for any value, we assume all the values are hashable and therefore acceptable as keys, it gives you the index. So this is very useful if you have to do a lot of, you would normally do a lot of this list dot index something, dot index something else. Every time you call index on a list, it has to basically start from the beginning and scan until it finds it. In this way, as long as there's no duplicates, you basically build it once and for all. If there is a duplicate value, then the later index will prevail because this goes from left to right. If you want the earlier one to prevail as it would in the method index, you need reversed. So you need to reverse the list. And that's not trivial. Yes?
Does reverse return a generator or a new?
Reversed returns an iterator.
Okay.
Yes, not a generator.
Iterator. Okay.
But it takes a sequence, not a general iterator.
But it doesn't.
No, sorted sorted can take anything, any iterable, and returns a string, a list, because there's no way to sort anything until you've seen all of it. You cannot emit the first item until you've seen all of them, because it could be that the last one is going to be first, according to the Gospels. And this is the way to build a dictionary from the keys and values using only built-ins. The zip takes the keys and values and makes a sequence of pairs, a list actually, and dict takes the list of pairs and makes it into a dictionary. And this is, okay, we start with a dictionary, and we want a list of the keys in the dictionary, each of them with its value. So sorted D takes the dictionary, meaning the keys, of course, and returns the sorted list, and we loop over it, and we built the list of tuples. So there's all sort of manipulation of this kind you can do, and the cookbook has an entire chapter called the shortcuts, exploring some of them. I've just picked 4 that I consider particularly significant. Sorting, of course, is very important. This woman is sorting coffee beans.
So on the previous slide,
Yes.
the sorted dict, could you, in most cases, do sorted items?
I don't remember ever doing so. It wouldn't make any difference because, well, it wouldn't make any difference in any sensible case. It's just extra effort. So comparison is lexicographic. So if you sort a list of tuples, and there is never any tuple where any 2 tuples where the first item is the same, then it's just a wasted effort to consider the second one.
Right. So,
And in a dict, keys are unique by definition.
right.
So there cannot be ever any consideration given to the further item of the tuple.
Right. So it should be equivalent without the. So you're not doing the extra list comprehension on the outside. Or if you just do d.items and then sort.
Oh yeah, that's another possibility. This is the fastest, very simply. So that's why I give it. At least it's the fastest last time I measured. It could be something else has been optimized recently for a sufficiently big dictionary. So, this is a very important feature of sorting is the key equals optional parameter. If you want some sequence sorted on anything except the natural lexicographic comparison of elements, you pass the key extraction function to either the sort method or the sorted built-in with key equals. So in this case, the sort, which is stable anyway, will happen on this modified version. This is basically a pre-cooked and highly simplified and extremely much faster version of the pattern which I used to call DSU, decorate, sort, and decorate. But you don't need to know that. Simply, this prints all the strings in their original casing, but they're sorted in a casing-sensitive way. So they're stable for, if you have a lowercase a animal and uppercase a animal, whichever one comes first in the sequence SS will come first in the output. And this is the classic quick sort in 3 lines taken from a scale. It's a divertissement because it's Python's own sort is much better, but it's fun to see, and it's the simplest way to teach quicksort. Essentially, quicksort means recursively quicksort everything that is smaller than the pivot, then add the pivot, and then recursively sort everything that is larger than the pivot. And this is quicksort. It's kind of more elegant in a scale. And of course, it's only 3 lines if you have a wide enough screen rather than these 30 characters I can fit here with a reasonable size font. There's several other containers in the standard library. Array.array is a very memory compact container for homogeneous arrays of elementary types, typically numbers or characters. You don't really use it much, but sometimes it can come in handy. Normally, you will go for third-party stuff if you really want to do big stuff with array of numbers. Multiple collections currently has only 2 collections, but they're really, really important. Q, a double-ended Q, and default dict, which is a kind of dictionary which, when accessed with an absent key, creates a value for it. Uppercase Q.Q is a thread-safe, first in, first out queue. We'll see it when we mention threading briefly. This is a mixing class for multiple inheritance to make a skeleton mapping into a rich mapping. Shelf is a persistent dictionary with some limitations. Weakref, if there's two things I really suggest as opposed to the elementary weakref things, which are the weak key dictionary and weak value dictionary. They're the references that are weak in that they don't keep an object alive. And I normally end up using weak value dictionary. Weak value dictionary, instead of keeping its values alive, if the value gets garbage collected, the whole entry in the dictionary goes away. Weak key dictionary is the same, but only works for hashable objects because it keeps. So, for example, if you're making a cache or something that needs to organize objects as long as they exist, but must not get in the way and keep objects alive when it should die, look into that. I also mentioned some support like copy, particularly the deep copy function. Bisect is for searching into a sorted list. Heap queue is for arranging a list into a heap or priority queue. There's many ways to do persistence. And then there's the absolutely precious Iterables, which we will get into in more details than just about any other method. So this is how you use default dict. You pass it a callable, typically a type, which can be called without any argument to provide an initial value for any key. So now to count something, which is the data structure normally known as a bag or multiset, you simply add 1 to b of k. But what if b of k wasn't there yet? Well, it gets automatically created by calling int without argument, which of course gives a 0. So this is the way to count stuff in Python. And this is how we print it. I'm using as the key beget, so the value is the key. So I'm printing, and I'm also asking sort to reverse. So I'm printing first those items which appear more often, and then decreasing frequency. So this is basically a histogram. Histogram, count an histogram in 4 lines, not too bad. If you want to union, add essentially bags, this is how you do it. You make a copy of one and item by item add the other. Note that we need to loop on the keys that are in the other bag. So they get added to 0 and the keys that are in the bag. For intersection, you want a new empty bag and basically loop on one of the bag, and if the key is also in the other bag, then take the minimum. You could do it without all of these precautions, but then zeros would be inserted in one of the bags. You have to be kind of careful when you make a default dict not to index into it with keys that may not be there, otherwise it grows. Because every time you index it, it gets a new, with a previously absent key, it gets a new item. Okay, this is how to build an index in a text file. In this case, I'm using set as the built-in type because basically what I want to do is connect to each word a set of line numbers in which that word is found. So I use the with statement that requires a from future import in Python 2.5. It will be standard in 2.6 because this way the thing gets automatically closed when I'm out of that statement, which is very handy. I enumerate the file so I get the line numbers. I split the line to get the words. And finally, I simply add this line number to whatever was previously there for that word. Of course, if nothing was there, then an empty set is created first and then added. So this has basically created my index. It's not a very selected index because every word goes there. And of course, it's kind of very rudimentary. I haven't bothered lowercasing the word, eliminating punctuation. So hello exclamation mark is one word, and so on and so forth. But it's just to show the idea. And then to display by alphabetically ordered word, you sort it and loop on the sorting. And you also sort the index so you don't print the pages in random order, but in nicely increasing order. Note, of course, that I use a comma at the end of the print to continue the line, and so I have to have a separate print when I'm done, so the line gets terminated. Iterables is one of my favorite modules. It's a very small but powerful collection of very fast, powerful, and general building tools for iteration. There are ones that build infinite iterators, meaning ones you have to break out of somehow. Count starts with a number and keeps increasing by 1 and gives the next one forever. Cycle, you give it a set of things and returns the first, the second, the third, the fourth, and then loops from the start and keeps repeating forever. Repeat, simply repeat whatever object you've given, either up to n times or forever. You can combine iterators. Chain, you give it some iterators and it does all of the first, then all of the second, then all of the third. Izip and imap, like zip and map, but without having to build stuff in memory, so you can actually work with infinite sequences. And then there's filters. Take an iterator and only return some of it. You can filter by predicate, when a predicate is true, when a predicate is false. As long as the predicate is true, and drop the part in which the predicate is true and then return the rest. You can use indices, slice the iterator. Take the first 4 items, take item from the 3rd to the 17th, take item from the 3rd to the 100 every 7, like any other slice. And star map, which is kind of obscure. T just makes replication, so you can T an iterator, advance on one of the T's, and the other one remembers the place. It's like a bookmark, so then you can go back and loop on it again. And group by, which given one iterator which tends to be sorted on something, it gives you an iterator of iterators which have that something constant. we'll see some example. OK, this is, I think, a reasonably cool recipe from the textbook. It generates all primes by the algorithm known, one of the most ancient algorithms known, the sieve of Eratosthenes. Now, most people believe the sieve of Eratosthenes is an algorithm to generate all the primes up to n, and you have to give it n in advance. This is not true. This is a sieve of Eratosthenes that just keeps going. Every time you call it, it's a generator, of course, it yields the next prime. How does it do that? Well, by keeping a dictionary which maps composite numbers that are to come in the loop to their first prime factors. So basically, it just goes from 2 onwards, 2, 3, 4, 5, 6, 7. That's what Iterables count does, trying to pop the entry from the dictionary. If there was no entry in the dictionary, then since this dictionary has all the composite to first prime factor, well, it was not a composite, therefore it was a prime, and so we yield it. And then we record in the dictionary the first composite to exclude, what is the smallest composite number whose smallest prime factor is q. Q squared. Has to be. Because if it was q times x for any x, either x is smaller than q, which violates one condition, or else it's not the smallest composite. So we only need to record one composite per prime we've found. What if p was composite? Well, then we need to get the next interesting composite into the dictionary in the A of x. And basically, we do that by incrementing by this p factor every time until we found one that wasn't in the dictionary yet. This may be a bit subtle, so let's add 2 print statements. This is what we print when we found a prime, and this is what we print when we found a composite. In each case, it's what was the index in the loop and what is the state of the dictionary this time. This gives you a good idea of how the thing works. I skipped the first couple because by the time we look at 3, which is prime, then we have, well, 9 corresponds to 3 and 4 correspond to 2. Those are the squares that we record first. Then we look at 4. Well, 4 is composite. We know because we found it here. And so we've removed it, and so we increment it by 2, and the next composite to exclude is 6. And then we look at 5. 5 is what we're yielding. So the next prime after 3. Again, we do the next. OK, so now what do we do with 5? We record 25, the smallest prime, blah, blah, smallest composite, blah, blah. And then we look at 6. Well, 6 was there, so 8 goes next as the next composite number to exclude whose prime factor is 2, smallest prime factor is 2. And so 7, great, that's prime. And again, I'll let you ponder through this and see why this happens at each step before we finally get 11. It's a very cool trick. And so now that we have the way to generate all primes, what if we only want some? Well, this is something you should never do, but I just needed to squeeze space. And Iterables is a long word, so I wrote, you could have import Iterables as I. Don't do it unless you have to program on slides. But and I also need a function to check if something is less than something else. It needs to be a callable. And I don't really like using lambda so much, so I gave it the name LT for less than. So let me get all primes such that they're greater than 100 and less than 130. Well, I want to read from the inside outside. I call Eratosthenes to generate all prime. I drop them while they're less than 100, and then I take them while they're less than 130. And so I get this. What if we want 7 primes that are greater than 200? Well, from the inside, make all primes, drop them until they're smaller than, I'm sorry, this should be 200 as typo here, and then slice the first 7 of this. It's a very high abstraction way to program. It's being compared to functional programming, and indeed, some of these, like take while and drop while, are terms you'll typically find in SML or Haskell. You reason at a very high level of abstraction. The cool thing about Python is that the higher the abstraction level you program to, given in good part, of course, the extreme care with which Iterables has been optimized, the higher your level of abstraction, the faster your program will be. Programs using these become really... the main author of Iterables, Raymond Hettinger, has been extremely helpful in writing the cookbook, and he's got this great introduction about why it's so fast and why you should really use it all the time. Okay, this is, by the way, the spiral of primes, which you're welcome to look up and explore with these tools. This is another way, I'm sorry, this should be green, iFilter. So anyway, this is a function which I'm building with a closure for simplicity. Last digit n returns a function that checks this argument whether its last digit is n, basically by taking modulo 10 and checking for equality to 10. So I want primes that are okay, between 333 and 555, and whose last digit is 7. Yeah, okay. Okay, this is one of the subtlest Iterables. It's group by. So what does group by do? Well, first of all, you tell it, okay, what's the key? What is the key of each record I'm handling? In this case, the key is whether a string is space or not. If space is a method of strings, it returns true for non-empty strings, which are all white space. So group these lines by the concept of whether it's a space. So basically, this gives me a group in this on which I'm iterator for each value, SG being the value of the key, and lines the iterator over all consecutive items that have that value for the key. Then when the key changes, that's a new group. So to make paragraphs from lines, I'm grouping by, I'm assuming paragraphs are groups of lines separated by empty lines. So when I group the lines by there being space or not, and I get SG, LNS. If not SG, so if the value of the key is not string is space, so the strings have contents, then I join, by default with this quote join method, the lines. Otherwise, I've just been given a bunch of empty lines, so I go to the next group. So this is an example to understand better what is going on. Take these lines. I'm using split lines, the split line method, because this way I can keep the \n. I can keep the end lines most easily. So split lines of by calling split lines of 1. So it's a list: A end of line, B end of line, C end of line, and so on, with a two new line one after the other, meaning an empty line in between, and therefore it's paragraph. And I call this Iterables group by, and to make it visible, I make a list out of it. It's only 3 things anyway. And see what it will be: false, some iterator, true, some iterator, false, some iterator. What does it mean? Well, I first have a group of lines which are not all white space, and then one of lines which are all white space, and then one of lines which aren't all white space, and so on. So every time the key value changes, I get a new group, which is something you find yourself programming often if you don't reason at a sufficiently high level of abstraction. You don't have to, but it's really, really much more fun. Okay, back to third party. There's plenty of containers. I singled out tables and graphs, but for example, order dictionary is something that's, but I want a dictionary, but it needs to keep track of the order in which lines have been put in it. Okay, so order dictionary does that. Oh, I want a dictionary which is always unique and keeps track of value key correspondence. I didn't have to build it. Well, two-way dict does that. I need an array of 1 billion bits. They must only take up 1 bit per. So use bit vector and bit buffer. Or there's also bit packet, which is a slight variation. Anyway, I want to iterate on an array. Use array iterator. And so on and so forth. I want an LRU. I least recently used cache. Use LRU cache. The containers are maybe the most interesting and well-fed groups of stuff. Okay, something I just couldn't skip, given that I wanted Anna, my wife, to lend me a hand on checking out my slides was, of course, there's a great way to deal with times, dates, and calendars. You've got several built standard library module and many third-party ones for date and time and for calendar support. This, in particular, is a Python support for the Maya calendar, which I think is extremely cool. It's not entirely complete. It's very old, from '99, but it's probably worth studying if you're at all interested in Mayan culture. Seriously, the cookbook has an entire chapter on this stuff. You basically want to use datetime, sometimes calendar, date util for very advanced manipulation, PyTZ for time zone support. And of course, if you want to support gcal and make it into Python calendars and vice versa, you can use the Google Calendar. If you want to use iCal, you can use iCalendar, and so on and so forth. So, just a check to see if I'm like totally. Anybody understand why I have this figure in a slide of this title? If anybody is willing to make a guess, please raise their hand. Okay. Yesterday, Today, and Tomorrow was an absolutely great Italian movie with Sofia Loren, Marcello Mastroianni, and I carefully picked one that wouldn't have Sofia Loren or Marcello Mastroianni because I thought I would make it too easy. Okay, sorry, too obscure. All right, so this is how you tell the date of today. This is how you tell the date of yesterday. You basically need to, and tomorrow, add or subtract not just the number 1, which would be kind of 1 what, would be kind of ambiguous, 1 day, 1 month, 1 year. You have to make a time delta saying explicitly you mean days or months or whatever. And this is the way to compute the date of last Friday, which is, again, is in the cookbook. In the cookbook, actually, the specification was very subtle. It's last Friday, but if today is already Friday, then today. And that I just couldn't fit on the slide, so I fixed the code. Yes?
So the syntax to this, it seemed to me, would be a little bit simpler if you would say today minus 1.day. So therefore, you could have 1.day. And
well, the syntax for this particular use might be simpler, but the syntax of the language would have to be totally perverted to manipulate that.
So unlike Ruby that has the ability for everything as an object, there's not the case in Python. We have
Everything is an object, but you can't change the methods of built-in objects. So with Ruby, if you want to make 2 + 2 = 22, you can. With Python, you can't. You know what? I like Python. And similarly, so in one dot word in Python, the parser says, OK, this is a floating point number followed by an identifier, which then is a syntax error. But 1 point is a floating point number. It's like 1.0, same thing. So, date of last Friday, for concision, to avoid repeating it, I make once and for all the 1 day time delta. And I start with a last def at yesterday, so today minus 1 day, as I showed here. And basically, I loop until I get to Friday. And Friday, as a constant, is defined in calendar. You could, like, hard code, I think it's a 5, but that would make it completely unreadable. Who remembers whether they start from 0 for 1 and whether they start from Sunday or from Monday? This is absolutely clear. OK, files. Very useful, particularly if you're ever in jail. The only built-in support is open. Open, there is a thing called file, which is a type, but don't use it. Believe me, don't. Use open. It makes a file for you. In the future, it will make more, better, brilliant stuff. Just use open. And basically, you can read, write, seek, and so on. But there's a lot of support for files in many ways. OS basically gives you access to whatever typically a reasonable operating system would support. Codex Open lets you read the file that use some encoding for Unicode and read them as Unicode strings. And many other things are supporting various formats of file. For example, comma-separated variables, gzip and bzip2 compressed and zip file compressed. Or they're supporting comparisons of file, temporary files, looking for input from several files, matching file names. Shutil, it stands for shell utils, it's not an immediately obvious name, is about copying, comparing, removing trees, entire trees of files, and so on. And of course, the third party has even more, including all sort of file format. Magic is like the file command in Unix uses the magic number, a pretty big array of magic number, given an arbitrary file to tell you what type it is, if it knows at all. FD send lets you send file descriptors between different processes in operating systems that support that. RAR file supports the RAR format, which is an ancient archive format you may have around. DBF pies support the DBF format, which was used by DBase 5 and other similar tools, and so on and so forth. So what is all in the standard library? Well, there's fundamental things, stuff that in other languages might be in the language themselves. Bisect, inspect for debugging, copy for copying, the collections we've seen, func tools for functional programming support, and so on and so forth. There's testing and debugging. There's processing of files and text more generally. There's persistence and databases, time and date support, something about numbers, and huge tons of network and web stuff. Network and web stuff is far too much to list. For many things, email, which just lets you receive and send emails, will be plenty, but of course, there's low-level networking support. There's support for HTML and XML as formats. There's a lot of support for protocols such as an NTP, SMTP. SMTP-lib is for client, SMTP-D is a daemon server, FTP, HTTP, POP, another protocol. WSGI is a standard implementation for advanced web applications. CGI is the old standard for web application, much simpler. URLib and URLib2 are for clients using URLs. XLMRPC-lib is a client, and this one is a server for the XMLRPC protocols. And there are so many handles on PyPy that I gave up. This guy, I don't know if you've noticed it. I was hoping he was in the audience, but apparently he isn't. Thinks this is the prettiest piece of Python. Essentially, he never can find wget when he sits at an alien machine. Maybe it's not installed, maybe it's not in the path. As long as he can have Python, he doesn't care if wget is there, because he can write it very simply, including a nice little hook function, which gets called periodically, once in a while, and prints what's going on, how much has been retrieved out of how much. And basically, your util retrieve does all the work. So this is in Guido's chapter, with Guido, the chapter Guido wrote the preface to in our Python cookbook. I decided, for the sake of this talk, to go a bit more complicated. Hey, but this thing gets the files one after the other. I want them all at once. I want them all now. Hey. So, Actually, it's not too bad. We import a lot of stuff, but then we make a queue. In that queue, we will post work requests, and we will have worker threads, 10, I decree exactly 10. Thou shalt not have 11, thou shalt not have 9, unless it is on thy way to 10. We start 10 worker threads, and then put in the queue all our URLs, and we're done. Actually, we'd better not be, we'd better wait for the threads to be finished, join the threads, but I didn't have an extra line to show the join call. And the reason we need to wait is that I set all the threads to be daemons, meaning they don't keep the process alive. It's like weak references applied to threads and processes. So I have a slight more detail in the hook, because I want to print a file name every time so the information doesn't get too mixed. And basically what a worker thread does is it gets the next work request. A work request is a URL, and then it does what the little thing did in Guido's program. So it's not too bad. There's a lot of overhead, but every thread is working independently. There is no need to worry about locking conditions. There is no shared variable at all except Q, which is thread safe by definition. So that's the only way you should ever do threading in Python. Or don't do it at all. This is a third-party thing called Twisted. It's probably too big to actually get into the Python standard library. But notice that it's concise and powerful enough that I've actually managed to squeeze in the from future import with statement. It implements a few crucial design patterns connected with multi-programming. I'm going to give a talk in September at the ACCU in San Jose about Python patterns for event-driven and multi-threading. You should just go to the ACCU California webpage. It's free night. Everybody's invited. ACCU is the Association of C and yes.
Third line from the bottom.
Whoops. You're right. I abused the keyword. Thank you. That was bad. OK. Let me fix that. Thanks. What? I missed that one. So anyway, the def being a reserved word, I was getting an error. So the point is there's this few design patterns, and then there's a lot of detail, protocol support detail, and Twisted has a lot of it. So client, well, it's actually Twisted Web Client, so it's an HTTP client. And it knows all the details of the protocol. You don't have to teach it. Well, it's HTTP 1.0. There's not really all the refinements of 1.1. But it's like URL-lib versus URL-lib2. But for most clients, it's kind of fine. So basically, in this case, we do, for every URL, we add the callback done to a deferred, which is the get page of that URL. So we accumulate the request, not on a queue which different threads will serve, but essentially on a list on which a select, or maybe a poll, epoll, or if we're on Windows, some devilish reactor implementation based on the Windows event loop, or whatever, will serve it as it may be serviceable. And basically, get page does all the hard work, just like the URL-lib, URL retrieve, and when it has all the information, it does the callback. Note that I can pre-bind a argument there, and this is the data which just gets written to the file object. Again, I'm using with, so the file object gets closed without me having to worry about such minutia. And so that's it. I giving the PDF URL again. just in case you forgot to write it down from the beginning. And I'm available for Q&A, although I think we only have 5 minutes. So sorry, I ran a bit over the normal allotted time. Any questions? Yes?
Just a URL, it's the Silicon Valley chapter of the ACCU.
Silicon Valley, not California, chapter of the ACCU. Thank you.
And it's accu-usa.org.
ACCU-USA, oh, that's the Silicon Valley. Is there a difference between the Silicon Valley and USA? .org. Anyway, that's in case you're interested. It's September 12th in San Jose. So, questions? Well, if there aren't any, then thank you very much for your patience and for letting me correct that little error on the fly. Thank you very much.